Good morning. Let us start the class. I was in a little hurry in the previous class to complete this particular set of slides, but somehow time ran out at that time. So I am repeating the same thing again for a few minutes now. We were in the process of finding out the upper cutoff frequency for the BJT, and these examples are selected from the textbook Malvino. In Boylstar textbook, he uses FL and FH as the symbols for low frequency and high frequency cutoff, whereas Malvino uses F1 and F2 for the low frequency and high frequency cutoff respectively. So in this particular exercise, we had already seen all the calculations what is performed at the right side. So in the last class, I was discussing the left side box here. For base side, F2 is obtained as 1.48 megahertz, and for the collector side, F2 is obtained as 4.96 megahertz. From mid-band, when we move to the higher frequency, base side has lesser value, hence upper cutoff frequency is considered as 1.48 megahertz. So this exercise indicates that the base side itself is going to decide the upper cutoff frequency. So please recall the basics. Screen is blank. Is it blank for everyone? Others also please respond. Nirmit, then refresh once again, because for others it is visible. Okay, let me continue. Fine. Please recall that when we move from 0 till infinity in the x-axis, we gradually move from 0 towards the maximum gain in the y-axis. So, whichever is the frequency which you obtain, which is very nearer to the maximum gain. That means when we compute the lower frequency cutoff, out of 3 frequencies, whichever is the highest frequency, that will be nearer to the maximum gain. So that we consider as the lower cutoff frequency. But in the case of upper cutoff frequency, it is just the reverse. Means we are going from the maximum gain towards 0 from the y-axis side. So then, if you have to mark the upper cutoff frequency, which can also be called as FH, which can also be called as F2. If at all we have to mark that upper cutoff frequency from the maximum gain, whichever frequency is immediately available to us as its value, that we consider as the upper cutoff frequency, because later on anyhow, the increase in frequency is not going to matter as far as the upper cutoff frequency is concerned. So for the base side and for the collector side, we have 1.48 megahertz and 4.96 megahertz. So naturally, we consider 1.48 megahertz as the upper cutoff frequency. So you can see, ignoring the lower frequency side, we can approximately say that the upper cutoff frequency itself is the bandwidth of the amplifier. So in this particular case, we can say that the bandwidth of this particular BJT amplifier is only about 1.5 megahertz approximately. So that is a very less value for the bandwidth of an amplifier, which means this particular amplifier cannot be used for the input signals which have the frequency more than 1.5 megahertz. So that's why I have been telling you that when we design amplifiers, we should design amplifiers specifically for an application. In such a case, the design becomes very critical, and the consideration of each and every component, whether it is the external component or the internal parasitic component, we have to consider all of them so as to obtain the upper cutoff frequency. As far as the lower cutoff frequency is concerned, we can always ignore it because it is hardly a few hertz or few kilohertz. We are always working with the radio frequency bands nowadays for all our communication applications. So in such a case, the value of the upper cutoff frequency becomes really very critical. Let me proceed to the next slide. I am almost coming to the end of this module now. I am only showing you the additional exercises for the sake of better understanding and better remembrance. Now the frequency analysis of the FET stage. Here in Malvino, he uses a slightly different symbol for FET. FETs have many particular symbols that are available. We generally follow the popular symbols in our lab. Whichever symbol can be easily written and whichever symbol can be easily understood, such symbols we use in the labs as such. Otherwise, textbooks can have many styles of symbols. So here you can see input voltage given is 50 millivolts and there is a source resistance 600 ohms. Then we have a 0.1 microfarad capacitor for input signals coupling. Then we have R1 and R2 as 2 mega ohms and 1 mega ohms. Now here the source is directly connected to ground because we can always connect it to ground in the AC analysis because of the bypass capacitance there. Then we have the drain resistance 150 ohms. Then we have a output capacitance of 10 microfarad. Then a load resistance of 10 kilo ohms. This is a voltage divider bias network using FET. Now for low frequency analysis, for the input side we have R equals Rg plus R1 parallel with R2. So that is 600 ohms plus 2 mega ohms parallel with 1 mega ohms, that is 667 kilo ohms. You might have observed a small difference here when compared to Boylstad and Malvino. The approaches are slightly different. Here he adds the source resistance along with the parallel combination of R1 and R2. Whereas in case of Boylstad, he had taken the Thevenin's equivalent resistance looking from the amplifier's input side towards the source side. Here in Malvino, he is directly looking into the amplifier from the source side. So there are many approaches. Which one is correct or which one is accurate, we cannot exactly come to a conclusion. The reason is, in most of the amplifier circuits, we are going to ignore the low frequency cutoff itself. We are only worried about the high frequency cutoff, and that is basically defining our bandwidth. So you need not worry about these minor differences. Actually, there are minor differences. Reason is, the source resistance is always a few hundreds of ohms. It will never come into the range of kilo ohms. That way it does not matter much there. Anyway, those are two different approaches. Now you may say when the source resistance is lesser, in the case of Boylstad's approach, when he takes all the Thevenin's equivalent, then everything becomes parallel there. That is going to make a difference there. But anyhow, as I have told, the low frequency cutoff is not very important for us when compared to the high frequency effects. That is why every textbook they will have different approaches. Actually, every authors will have different approaches. And it is up to the user or up to the designer to have the feasible approach. When we are going to design an amplifier, we will have to practically simulate. At times we may have to practically measure all the parameters before finalizing the amplifier's design. Until then, we can follow all these theoretical approaches. These are all basically theoretical approaches. So now, for the input side, the resistance is obtained as 667 kilo ohms, and hence F1 equals 1 over 2 pi RC, where C is only 0.1 microfarad there. So we get F1 as 2.39 Hertz, or the lower cutoff frequency as 2.39 Hertz. Now for the output side, R equals RD plus RL, that is 150 ohms plus 1 kilo ohms, or 1.15 kilo ohms. So we get the lower cutoff frequency with reference to the output side as 1 over 2 pi RC is 13.8 Hertz. Now you can see 2.39 Hertz is there, 13.8 Hertz is there, As far as the lower cutoff is concerned, we consider the highest frequency here. So we consider 13.8 Hz as the F1 or FL. Therefore, from the midband, when we move to the lower frequency side, the dominant low frequency cutoff value is F1 equals 13.8 Hz. Lastly, I move on to some exercises along with the FET's high frequency analysis. Now, for the high frequency analysis, we had already seen that we have CGS, we have CGD, and we have CDS. Now, we will have a Miller's counterpart there. We can express it as CGS with respect to ground, whereas CGD here, and we can have these two types of approaches now, as I will elaborate now along with the text. The FET has three internal capacitances, CGS, CGD and CDS, but these are difficult to measure, and therefore the manufacturers list the capacitances under short circuit conditions. Hence, for the input, output and feedback parts, the internal capacitance can be listed as CISS from the input side is CGS plus CGD, and COSS from the output side is CDS plus CGD, and then we also define one more CRSS, that is called CGD, gate to drain, that is working here as the feedback capacitance. Now please note, this is the approach that is followed by the Malvino textbook. As I have been telling you, don't worry too much about all these approaches. You have to follow the PDF copy which I have posted in the Google class. We take Boyle-Stud only as the material for our evaluation as well as for final exam also. But I am showing you that there are approaches possible other than Boyle-Stud also. That way, no textbook is 100% all right. At the same time, no textbook is wrong also, which means even the authors are basically scientists. The way in which they conduct experiments, the way in which they hypothesize, that is the way they follow. And again, European community has a different approach, American community has a different approach. We being Asians are following both the approaches. That is how we Asians are following it, because we are using both the technologies, American as well as European technologies. That way, this is another approach followed by Malvino. So, by utilizing the data provided by the manufacturer, the internal capacitance can be written as CGD equals CRSS, CGS equals CISS minus CRSS, and CDS equals COSS minus CRSS. Instead of all these approaches, we can straight away go into the Miller's approach also. That is more suitable, but Malvino has followed this approach. Using CGD, the input and output Miller capacitance also can be written C in with Miller as CGD into AV plus 1, and C out of Miller is CGD into AV plus 1 divided by AV. It is writing the Miller's equation in a opposite manner, or writing the same Miller's equation in contrast with the approach which Boyle-Stud had used. But the net result is the same always. The voltage gain for the common source amplifier is given by AV equals GM into RD, where small rd is equal to capital RD in parallel with capital RL. This we are already familiar. Let us have the last two exercises using this particular approach. Exercise for obtaining F2 or FH for the given FET circuit. Given CISS is 60 picofarad, COSS is 25 picofarad, CRSS is 5 picofarad, and GM is 97 millisiemens. Now, using the approach which was discussed earlier, we get CGD equals 5 picofarad, CGS equals 60 minus 5 is 55 picofarad, CDS equals 25 minus 5 is 20 picofarad. Now, using all these values in the formulae, we get the voltage gain as 12.1, and the Miller's input capacitance is 65.5 picofarad. Now, for the gate side, we get total capacitance is CGS plus the Miller's capacitance is 120.5 picofarad. Now the net resistance at the input is Rg parallel with R1 parallel with R2, it is around 600 ohms. Now for the drain side, we get the total capacitance using the Miller's counterpart as 25.4 picofarad. And this small Rd is given as capital R in parallel with capital RL. This is the notation used by Malvino for computing the output resistance. Now again, don't get confused with the small Rd with the drain resistance which we had used earlier. The notation is different with both the authors. That is the problem we follow or problem we face sometimes when we have this teaching learning process. But don't worry much about this. This is only for the sake of illustration, not for the sake of evaluation. So finally we get small Rd equals 130 ohms. Using all these values, for the gate side we get F2 or Fh equals 2.2 megahertz. And for the drain side we get 48 megahertz. Now which one we have to take? Obviously 2.2 megahertz. From the midpoint, when we move to the higher frequency side, the dominant higher frequency cutoff is 2.2 megahertz. So the approximate bandwidth of this amplifier is around 2.2 megahertz. With that, I am coming to the end of module 3. Okay, let me stop sharing this PPT. Let me start module 4 now. I hope you can see this. I will slightly zoom. No, let me zoom in again. The name for the module 4 is feedback and oscillators. In module 1, we discussed the basics of BJT, DC and AC analysis. In module 2, we discussed the FETs, DC and AC analysis. In module 3, we discussed the low frequency as well as high frequency response of both BJT and FET amplifier circuits. Now we move on to another important circuit part called oscillators. Now this module is named as feedback concepts along with oscillators. So first let us discuss feedback only. Before that, I'll have to tell you that we use amplifiers for gaining a larger signal power or larger signal strength or larger signal amplitude for a given smaller signal input. Whether that frequency range is in the audio range or in the radio range, we are going to design amplifiers for the given frequency range for obtaining the required voltage gain or power gain. That is the purpose of amplifier. Now what is the meaning of oscillator? Oscillator is the one which produces a fundamental frequency. For example, you're all listening to FM radio. In the FM radio, we have so many FM radio channels such as FM Rainbow, Radio Mirchi. There are so many. I typically remember FM Rainbow only predominantly because I mostly listen to only that particular radio station. Whereas there are many, I think more than 10 radio channels are available here in Bengaluru itself. I don't know about your particular areas there. But anywhere there are minimum 10 radio channels available. There are many different companies which are using these radio channels for broadcasting music or news or any other information as such. Now, when you listen to FM radio, let us say you are listening to FM radio channel where they keep on saying their carrier frequency. Let us say a particular radio channel keeps on telling 92.4 megahertz. if they keep on saying 92.4 megahertz or maybe 92.3 megahertz also, let us say they say 92.4 megahertz, then it means that that is the radio carrier wave which is actually carrying the music signal. You already studied about modulation in first year. Modulation is the process of superimposing a low frequency information signal on a high frequency carrier signal. Just like we are all low speed human beings, we sit on a high speed vehicle, either a two wheeler or a four wheeler, or even a train or even a flight. We sit either on or inside a vehicle. That vehicle is a high speed carrier now. It is going to carry us from the source till the destination. In the same way, we are going to use a high frequency radio wave as a carrier wave for carrying the low frequency information signal. And that information signal can be voice, it can be sound, it can be music, it can be text, it can be data. It can be analog also, it can be digital also. Now, if that carrier is required for carrying the information signal, how do we generate the carrier is the question now. For generating the carrier, we use the oscillators. So, amplifiers and oscillators are the two basic building blocks of any electronic communication system. So, in this module, we are going to discuss initially the feedback concepts. Later on, we are going to discuss the oscillators. So, with this brief introduction about oscillators, let me start this particular module. Just for a change, I am showing you the pages of the textbook itself. Even though I have written the notes, for this particular module in the beginning, I had not written a very organized notes. My notes is still there with me, but it is a crude notes in the sense my handwriting is not really very good. I had roughly worked out because this was supposed to be a chalk and talk lecture in our classroom. But anyhow, because of this online mode, for a change, I am going to show you the pages of the textbook itself. At least you will see some pages of the textbook. Otherwise, I am not sure whether all my students will read the textbook or not. Mostly they depend on the notes or mostly depend on the PowerPoint. So let me discuss this particular module's beginning using the pages from the textbook only for some few initial classes. Later on, anyhow, whatever notes I have written, I am going to put all that into my PowerPoint slides, and after a few classes, I am going to start my PowerPoint slides only, where every data is available there. So you don't have to worry about whether I pass the notes to you or not. I am going to pass on everything to you gradually in the future. But as of now, let me show you the textbook's page itself. This textbook is Boyle Start textbook. I will not go through all the sentences here, but I am just going to show you this diagram, and we are starting with the feedback concepts. Now let me zoom so that I will show you only the diagram. Okay, now you can see this diagram. So at the middle, we have this A. A is amplifier, and I had already told you why the amplifier symbol is like this. In the first module itself, I had told you. Anybody remembers? If anybody remembers or recalls, you can tell me why this amplifier symbol is like this. Can anybody tell? Okay, let me tell. As no one else is responding, let me only tell. Okay, Nirmit is telling the inputs are in voltages. No, that is not the answer. Inputs are not just in voltages, inputs are in currents also. And for the feedback, no. We are not discussing feedback. Feedback I will discuss later on. My question is why the amplifier symbol is like this. That was my question. Why this amplifier symbol is a triangle like this? That is my question. So the answer is, let me stop annotating. I just showed you the amplifier symbol. The answer is, we have computed the input impedance as well as the output impedance for all the amplifier circuits. Ideally, the input impedance must be infinity and output impedance must be 0. Now, we may not get that particular characteristic in any one particular amplifier. That is why we always club multiple amplifiers. So, together, when we have a multi-stage amplifier, imagine, then input impedance is very high, output impedance is very low. That is the indication here. When the input signal is coming, it will see a wall here. Means it is going to see a wall, which simply means that amplifier is not going to take any input signal's energy into it that way. If amplifier uses the energy of the input signal, then the input signal already is weak, it will become weaker. So, amplifier should have a very high input impedance such that signal only will enter into the amplifier. Signal's energy will not be utilized by the amplifier at all. For the working of the amplifier, it will derive its energy only from the power supply. That is why ideally amplifier should have a very high input impedance. At the same time, ideally an amplifier should have a very low output impedance, or ideally 0. Ideally Zi must be infinity, Z0 must be 0. That is the indication of this triangle symbol. Generally, engineers, we use lot of symbols in our lives, in our professional lives, and each symbol will have a distinct meaning there. So, if the output impedance has to be ideally 0 or practically it has to be very less, which simply means whatever load we connect here at the output, the amplifier must be able to supply that much of energy or power to the load. Now, from where will the amplifier derive all these energies to give it to the load? Again, obviously, amplifier has to derive all this energy from the power supply itself. That is why the amplifier symbol is a triangle here. Now, when you put a bubble here, you will show it as inverter. In the digital electronic circuits which you are studying, you will always write inverter with the triangle and the bubble. What does it mean? Inverter is nothing but an amplifier with the logic state of 0 and 1. That means if you use the amplifier exactly in the active region or in the middle of the load line, which we also called as quiescent point, now that is working as an amplifier. Otherwise, if you use the same transistor in the cutoff region and in the saturation region for the sake of BJT, or in the cutoff region or in the ohmic region for the sake of JFET, then that is a digital circuit. Then we simply put a small circle or bubble here indicating that it is an amplifier which is used as an inverter or amplifier which is used as a logic gate. Otherwise, internally the device is the same. It is the transistor itself which we are going to use as per our application. Now, instead of bubble, if we leave it as it is, what is it called in the digital electronic circuits? Here we call it as amplifier in the analog electronic circuits. If in the digital electronic circuits also you use the same symbol, what is it called? Can anybody tell me? Not gate. No, it is not not gate. Not gate and inverter are one and the same. If you put a circle or bubble here, then it is a not gate or inverter. Both are one and the same. My question is, when you don't put the circle, let us say you use this triangle as it is in digital circuits, then what is it called? Is my question. Pass gate. Okay, pass gate is also fine. It is not op-amp. Op-amp is something different. Op-amp will have two input terminals. Op-amp will have plus and minus. It is not op-amp. And pass gate is to some extent correct because it is passing the signal as it is. But there is another name for that. Another name is called buffer. Simply it is called as a buffer because even in the digital circuits, digital signals also will have loss when they pass through the wires. So whenever there is a loss of digital signal, it will be passing through a buffer so that the signal's original amplitude will be reconstructed through the buffer. So even in digital circuits we use this symbol, but there it is not an amplifier, there it is a buffer where it will have a gain of unity, means whatever is the input signal that will be produced at the output signal, it is basically a digital signal there. And there will be no inversion at all, signal goes as it is. Fine, let me come back to the analog circuits now. We have this amplifier, now we have a concept called feedback. Portion of the output signal we take it through one feedback circuit, and then that portion of the signal we connect it back to one more circuit which is a summer. Here the summer has two distinct symbols, plus and minus, means we are using this feedback signal at the input to be subtracted from the input signal. You can see this plus and minus symbol, which means, let us say I take some 10% or 20% portion of the output signal by means of this another circuit called beta. Beta is nothing but a passive network. You don't have to worry about what is this beta. It is a passive network. It can be simply a resistive capacitive network. It is only used to sample a portion of the output signal. Now obviously Vf will be much less than V0. Vf is the feedback signal, which will be much less than V0. Now this Vf, we use it just as to subtract from the input signal Vs. We are giving the input signal as Vs. Vs means signal from the source. Now we subtract this Vf from Vs and we get this Vi. Vi is the actual input to the amplifier. Now you may see that Vi equals Vs minus Vf. Now voltage gain equals V0 by Vi. Voltage gain will not be V0 divided by Vs. Understand that? Amplifier's voltage gain is V0 divided by Vi. The net voltage gain is V0 divided by Vs. But what is happening here is, we are not adding the feedback signal. We are subtracting the input signal from the input. That means, let us say we use, let me write something here just for you to make it clear. Let us say we give 10 millivolts here, and let us say the feedback signal is 1 millivolt here. Imagine that way. A small portion of the output signal we are taking out. Let us say the feedback signal is 1 millivolt. Now Vi is 9 millivolt. Okay, Vi is 9 millivolts. Let us say the gain of the amplifier is 100. If the gain of the amplifier is 100, we are going to get the output as 900 millivolts. We are going to get the output as 900 millivolts or 0.9 volts. Out of 900 millivolts, we take back 1 millivolt as the feedback. And that 1 millivolt again we feed it back to the input. Now always Vi will be less than Vs, or Vi will be Vs minus Vf. Vf is some percentage of V0. That is decided by beta. What is this beta? Beta is the feedback factor. Now don't get confused with the beta which we have been till now using. That is why in engineering there are so many symbols which are used at multiple places. Till now, whenever we discussed beta with reference to BJT. That was IC by IB, collector current by base current. Now in this module, whenever we discuss beta, we are not discussing a circuit level, we are discussing a block level now. Till this module, we have been discussing only the amplifier circuits. From now on, we will be having a discussion of block level explanation in module 4 and module 5. Oscillator is a block which comprises an amplifier inside. That is the idea. Now, whatever block diagram I am showing you, this is not an oscillator. Don't get confused. This is not an oscillator. Later on, I am going to talk about oscillator. Right now, we are discussing something else which is called negative feedback. Now, look at this. This is called as negative feedback because feedback is subtracted from the input. If at all feedback is added to the input, then that is called as positive feedback. All the oscillators are using positive feedback. That we will see later. Right now we are discussing negative feedback. Now you may immediately wonder, if this is negative feedback, what is its advantage? Yes, there is an advantage also. I had discussed about gain bandwidth product. Please recall that particular curve where I had mentioned two particular curves, one with the larger gain, one with the lesser gain. And we had seen that when the gain is reduced, bandwidth is increased, right? So here we can see, because of the negative feedback, now gain is reduced. Just look at this. If this feedback was not there, then the output would have become 1000 millivolts, right? If this feedback was not there, output would have become 1000 millivolts because the gain of the amplifier is 100. 10 millivolt would be directly given like this. 10 millivolts directly given here. Gain of the amplifier is 100. So 100 into 10 is 1000 millivolts. That would have been the case without the feedback. Now with the negative feedback, gain is reduced now. Instead of 1000 millivolts, we are getting 900 millivolts. Even though the amplifier is the same, we are applying a portion of the output signal back to the input signal with the opposite sign or by subtracting it from the input signal. So the gain is slightly reduced. But we had seen earlier that when the gain is reduced, bandwidth is going to be increased. Now this is the first advantage of negative feedback. The first advantage of negative feedback is that bandwidth can be increased. As we know that gain bandwidth product is constant for a given amplifier. Please recall whatever I had discussed in the previous module also. The gain bandwidth product for a given amplifier is a constant number. Now if you want to have a increased bandwidth, we have to reduce the gain of the amplifier. For reducing the gain of the amplifier, we go for a negative feedback. So that way, this beta is the feedback factor. It is not the current gain of the transistor because we are using beta for a block now. We are not using beta for a device now. You will have to remember this always. Now this A is the gain of the amplifier. Now this is what the approach which Boylestad follows. In Malvino, he has slightly gone to a different approach where instead of beta, he uses the symbol directly capital B. He uses capital A for the gain of amplifier. He uses capital B for the gain for the attenuation, not the gain. Attenuation which is occurring in the feedback circuit. There is no confusion that which one is this beta. So there he simply says A and B. That is his approach. Whereas we have the Boylestad book only as our main reference now. Actually, that is one of the very good books for this analog electronic circuits. Both are really very good books. Both Boylestad and Malvino are very good books. In fact, you can keep this Malvino book lifelong with you. Electronic Principles by Malvino. You will have to keep reading that particular book, not only for analog electronics, for general basics of complete electronics. And at the end of every chapter, he has got a multiple choice questions. You can try out all those MCQs, even answers are given at the end of the textbook. You can always assess yourself and it will help you even when you come to third year and final year. It will help you for your placements also. Even if some of you are having an aspiration to write GATE exams also, for that also, Malvino book also is going to be useful. Boylestad book also is going to be useful. That is why these are really very good textbooks for analog electronic circuits. That is why we had chosen these two books as our syllabus books, or reference books, or textbooks. Fine. So, right now let us follow the convention which Boyle-Stud only uses. Now let me stop annotating. Till now whatever I have been telling you, the obvious advantage of negative feedback is gain, even though it is reduced, bandwidth is increased. Now that is the purpose of negative feedback. Now this is a feedback amplifier. Now remember, Vi is Vs minus Vf, and Vf is a portion of V0. So we can write Vf as beta into V0. Let me write it here, just for you to remember. Vi equals Vs minus Vf. Okay. Now, what is A? A is V0 divided by Vi. A is the gain of the amplifier, that is V0 divided by Vi. And Vi is, as per this block, Vs minus Vf. What is Vf now? Vf is beta into V0. See, this beta is a small factor by means of which Vf is obtained. Let us say if beta is 0.1, then Vf is 0.1 of V0. That means Vf is 10% of V0. Just like this V0 is, we can write V0 is A into Vi. Just like we have written A is nothing but V0 by Vi, or V0 can be written as A into Vi. In the same way, Vf can be written as B into V0, because the signal is moving in this direction here, whereas the main signal is moving in this direction here. Portion of the signal is coming back. So please remember these main three expressions. Now using these three expressions, later on we are going to derive a formula completely for V0 by Vs. Now we have to find out what is V0 by Vs. Okay. The net gain of the total block with the negative feedback amplifier is what? That we are going to discuss in the next class, because already time is running. I will not be able to cover up that particular derivation. But in the next class, we will see what is V0 by Vs. It will be obviously less than A, right? V0 by Vs will be obviously less than A, because the gain will get reduced. That is the obvious disadvantage of negative feedback, but the obvious advantage is bandwidth gets increased. Now, along with the increase in bandwidth, we will have increase in input impedance. That is another advantage. And we will have decrease in output impedance. That is another advantage. How is it going to happen? Let us see in the next class. That is where we have a mathematical analysis of this negative feedback circuit. So, I will see you again in the next class. But until then, you please remember V0 equals A into Vi. Va equals Vs minus Vf. Vf equals beta into V0. Using these three, we are going to find out V0 by Vs. Later on, we will find out Zi also for the circuit, Z0 also for the circuit. And then we will have a count of what are all the other advantages with the negative feedback in spite of the reduction in gain. We will see that in the next class. See you in the next class. Until then, take care and goodbye.